Okay, so if there are no questions from last time, then let me continue. So towards the end of the lecture last time, we saw that in a one-dimensional spin system, let's say the XXZ spin chain that we were talking about, if we introduce a sufficient amount of disorder through some random magnetic field, then it basically stabilizes a many-body localized phase. And that many-body localized phase has some very funny properties in the sense that all its eigenstates, actually almost all its eigenstates, have area law entanglement. And secondly, there is a concept of an emergent integrability because there are these dressed operators which emerge. And these dressed operators are localized in some sense, and there is an extensive number of them. And if you actually figure out all those extensive operators, they all commute with the Hamiltonian. And so there is a emergent integrability there. Okay. So then, as I was saying in my sort of motivation for fluke physics, in particular, how to get non-trivial physics. So of course, this MBL phase is a very good starting point because this is a highly non-ergodic phase of matter, right? All the high energy eigenstates here have area law, okay? And that's related to the fact that if I create an excitation, a local excitation on top of a high energy eigenstate, that excitation only sort of travels a bit through the unitary dynamics. Okay, so then we can ask, if I sort of use a fluke structure on it, introduce periodic drives on a many-body localized system, maybe it does not immediately go to infinite temperature. Maybe there's a regime in which I get a fluke version of many-body localized phase, and that's actually indeed true. So, for example, you can look at these two papers. In particular, I've taken this figure from the first paper, in which they show a periodically driven version of a problem with strong disorder. So essentially, the unitary operator, the fluke unitary, has two parts to it. Okay, the first part has this disorder in it. Okay, because these HIs are random. And the second part is some translational invariant part. Okay. But of course, we know that if the disorder is strong enough, if we don't drive this problem, it's in an MBL phase in one dimension. That's what we learned yesterday. Now the question is, if I introduce this unitary, sort of fluke structure, then does this fluke MBL survive? Okay. So one way of looking at it is something called level statistics again, which we have sort of briefly talked about, and you also heard it in more detail in one of the tutorials. So the essential idea is that you calculate something like expectation R, which you can actually calculate knowing the eigenspectrum of your problem from, let's say, exact diagonalization. And that's what these authors also did for these system sizes. And then this expectation R goes to some value like 0.53, something like, sorry, 0.534, something like that for a thermalizing system. But whereas for an integrable system, it goes to something close to 0.38. And that's because there is a Poisson statistics for integrable systems, and it's something else for the thermalizing systems, right? Now, this many-body localized system, even though it's an interacting theory, it's because it has an emergent integrability, should show Poisson statistics. Okay, and one can actually check that numerically. Okay, so here you see that here everything else is fixed, and let's say this T1, this time scale T1 is tuned. Okay, now you see that when this T1 is small, the system indeed looks MBL. But this is not a static MBL, this is a fluke MBL. Okay, whereas as you keep increasing T1, there seems to be a phase transition here, okay, indicated by these crossings. And then after you reach a sufficiently large value of T1, it seems to go to a thermal phase. Okay, so there seems to be a distinct phase transition. Let me call that T1 star, below which the system is in fluke MBL, above which is in the thermalizing region. So the moral of the story is, if I take an MBL system and I drive it at least at very high frequencies, then it stays NBL. It of course becomes a fluke NBL. Okay, so there seems to be an interesting phase transition here. And the authors looked at several other things. For example, this is something which I didn't have the time to discuss. They in particular looked at how the entanglement entropy grows. Of course, you start from a simple state which has a low entanglement. And let's say you're looking at the entanglement entropy of the half chain, the half of the system size. So you integrate half of the degrees of freedom, and then you look at the entanglement entropy of the rest. Then for a thermalizing system, this entanglement entropy grows linearly in time. Here it's n because it's a fluke system, and then it saturates to some value depending on what your system size is. Okay, whereas for a many body localized system and its fluke version, actually the interesting bit is that the growth is logarithmic in time, so it's much slower than for a ETH respecting fluke system. Okay, so here you can see that because this is on a you can see this is on a log scale, so there is a logarithmic growth of entanglement in time in this fluke problem. Okay, and an interesting question is, remember I told you that the fluke Magnus expansion sort of diverges immediately in the thermodynamic limit if you take a generic system and introduce a fluke structure there. Now the interesting question here is, here we see sort of a phase transition, right? Here we see sort of a phase transition here, and in particular at very large drive frequency or for very small T1, the system is localized, many body localized. Okay, so then the question is, does the fluke Magnus expansion have a finite radius of convergence in this case? And actually the answer to that is not known, but it's an interesting thing to think about. So exactly like in the static MBL, for at least the fluke MBL case, again, one can in principle find these dressed operators such that they commute with each other. They are sufficiently localized in space. That's why I can index them by site indices like that. And they also commute with your fluke unitary. So again, there is a emergent integrability structure when you consider the fluke version of an MBL. And so from now on, I'll call that fluke MBL. Okay. So far, so good, I hope. So now we come to time crystals, which is going to be sort of the main player in the rest of the lecture today. Okay. So what are these time crystals? Okay. So this phrase is very provocative and was introduced originally by Wilczek. And of course, it's sort of chosen to sort of indicate breaking of time symmetry, time translation symmetry in a spontaneous manner, exactly like space crystals break spatial symmetry in a spontaneous manner. Okay. However, it is well known that in equilibrium, you cannot break time translation symmetry spontaneously. The reason for that is the density matrix looks like this, right? And assuming that your Hamiltonian is independent of time, basically this density matrix would also have this property. So you cannot break time translation invariance, okay? But of course, let's first recap usual things, because you will see that it will really help us understand these time crystals in a nice manner. Of course, we cannot break time translation symmetry in equilibrium, but we can break other symmetry in equilibrium, right? I mean, we know many examples. For example, in an Ising model, we can break the up-down symmetry, the Z2 symmetry, right? In a quantum problem as well. For example, the transverse field Ising model in one dimension does that, right? That's an analytically solvable case where that happens, right? So, okay. So then the question is, how are symmetries other than time translation broken in equilibrium? That's a perfectly genuine question to ask. So I think this is sort of known to many of you from your graduate school, but I'll still sort of highlight some points because it'll be useful to discuss time crystals. So you see, this is your density matrix. So by definition, the density matrix preserves all the symmetries of the Hamiltonian, by definition, because it's a function like this. But then that would suggest that no symmetries of the Hamiltonian can ever be broken, because this is your density matrix, and I take any operator, the expectation value of that operator is trace of that operator times rho, right? So if rho preserves all the symmetries of H, then there seems to be a paradox. But this resolution of this paradox is well known for symmetries other than time translation. So for example, let's consider our favorite problem, because this is very simple. Let's consider a Z2 Ising ferromagnet. Okay, for example, just as a toy model in your head, you can just think of the 1D transverse field Ising chain, right? So in a finite system, let's say you're doing exact diagonalization, or let's say you're doing the analytic answer at a finite system, which you can do using your Jordan-Wigner fermions, then what you see is that basically there are two almost degenerate states, and they are separated by a gap to the rest of the states. And these almost degenerate states look like this, right? So a linear superposition of all up with all down, and there are these phases, okay, plus or minus, right? And these states, these two states, of course, respect all the symmetries of your Hamiltonian. They respect the Z2 symmetry of your Hamiltonian, okay? They don't break it. But please note that these states are long-range correlated cat states, okay? So why are they long-range correlated? The answer is very simple. Take any local correlation function. In particular, you can take magnetization, the Z component of it. So let's say you measure this 2-point correlation function on this state. There's a plus or a minus. Just choose any of them and just measure this 2-point correlation function, and just measure and look at the connected correlation function. Connected correlation function. Then you can easily show that for this kind of a state, this connected correlation function does not go to 0, even if these 2 points x and x prime become spatially separated. Okay, so they are long-range correlated states. Okay, but they're also highly unstable states, because they are sort of macroscopic cat states, right? Because this is a state, and this state is completely different macroscopically from this state, right? Because I can go to any local site or some other local site, and I immediately know that this state is macroscopically different from this state, but it's a quantum linear position of these things. So this is a macroscopic cat state, right? So these are sort of highly unstable states in a lab, right? Whereas the physical states are basically this guy or that guy, right? And the physical states are, of course, short-range correlated by this above definition, in the sense that the connected correlation does go to 0, right? But the physical states break your Z2 symmetry. But the resolution to the paradox is very simple. In a finite size system, if you start with this physical state, it will take an exponentially long time in the system size. It will take an exponentially long time in the system size to tunnel to this state. Okay, that's because the splitting between this guy and that guy is exponentially small in system size. Okay, so if I start with this physical state and I wait for a long time, this physical state would go to this state and then it'll go to something else. But that tunneling time is exponentially long in system size. Okay, right.
Arnab,
Yeah.
so why do you say that the cat state is unstable in the lab?
The macroscopic cat state is unstable in the lab, because imagine that in the lab there is some coupling to some kind of a bath, no matter how weak, right? And that bath sort of does some sort of projective local measurement. Then it would immediately choose up over the down or down over the up, right? So I mean,
so you're saying like any small dissipation, or like bath, coupling with the environment will make it very fast, is it?
Yeah. Because I mean, just imagine that. Just imagine that there is something happening in the system from the external environment, and it's like a projective measurement at some site, and then that particular site collapses to the up state, but then you definitely know that the entire system would be in this state, right? Or with 50% probability you can do that. So this would immediately collapse. Yeah.
Okay.
Yeah.
Okay.
Yeah. Yeah. So these states are inherently unstable to coupling, as far as I know, macroscopic cat states. Okay.
Right.
Yeah. Okay. So as I said, the physical states break Z2 symmetry, but they just take a humongously long time scale to sort of tunnel to their partner. And that's this well-known phenomenon in phase transitions and statistical mechanics of ergodicity breaking. We also see that in Monte Carlo simulations all the time. Suppose I do a simulation of an Ising model below its phase transition. Of course, in Monte Carlo, I'm taking a finite size. So there is no way I can break a symmetry, strictly speaking, right? But if you again try to estimate this quote unquote tunneling time, you will see that it goes exponentially large in system size. And so if you take a reasonably big system for all practical purposes, you can just consider the time scale to be infinity. Okay. So now the question is, does this kind of intuition, now I'm asking the question, does this kind of intuition work for time crystals? That's the sharp question. And we will soon see that the answer to that would be yes. But of course, it won't work in equilibrium, or therefore it won't work for a quench problem. But we'll see that it'll work for a fluke time crystal. So it'll work in a fluke setting. So in a fluke setting, of course, we don't have continuous time symmetry. We have a discrete time translation symmetry. So the time translation symmetry is t going to t plus t. And we'll see that this would be spontaneously broken. And we'll see that it'll be broken exactly in this sense. Okay. So I hope there's no confusion here. If there are any questions, you can ask me. I mean, yeah. If there's any confusion about this part that I said, you can ask me. Okay. So if there are no questions, then let me go on. Okay. So now, so let me go over this step by step. So what are fluke time crystals? Let me first define them. Okay. So here I sort of cite the original papers which got this concept and first introduced it to us. Okay. And I especially like this paper because it's very sort of lucidly written, the first one. Okay. So yeah, so what's the definition? So I adopt two definitions and both of them are equivalent to each other. And it'll turn out that for my purposes, the definition 2 would be sort of a nicer definition. Okay. So you see, when we were talking of fluke systems, the first thing that we said was, suppose I have a many body system and I am driving it periodically. Then if I look at local properties stroboscopically in time, then I see that the local properties synchronize with the frequency of the drive. That's one of the first things I said in a many body system. Okay, so here for a time crystal, actually what you would see is that the system would fail to synchronize with the drive period in a very precise manner for all physical initial conditions. So here I'm using the phrase short range correlated, but you can just imagine in your head for all physical initial conditions, or for initial conditions which you can sort of prepare in a lab in a reasonable time scale. Okay, so so that's the idea. I mean, if you try to prepare this state in a lab, I don't think you can sort of make this kind of a state in the lab in a sort of a physical time scale. Whereas, of course, this other state is very easy to make in a lab. Okay, so yeah. Okay, so you start with some reasonable initial state, as I have always tried to stress. Okay, with small entanglement and all reasonable properties, and then you just do your quantum evolution. So this is the answer from your quantum evolution after some whatever. So this is bad notation. Maybe I should have written NT here, but sorry, I'll change that later. So basically, you wait for a while. After a sufficiently long time, you just wait for all the transients to be over. So there should be NT here because you wait for a reasonable while. And then what you see is that, oh, actually, no, sorry, I take back my thing. I have been reasonably careful. So this T1 is large. Yeah, okay, so this is fine. This T1 is large. So you wait for a reasonable amount of time. And then, of course, if the system would have synchronized, then you would have seen that this thing is equal to this thing. That's the meaning of synchronization. Okay, that's the meaning of synchronization, if this T1 is large. Okay, but here you will see that there will be at least some local operators. There will be at least some local operators which does not satisfy this condition. Instead, what would happen is that there will be some integer n naught greater than 1. And of course, the simplest case is n naught being 2, where this equality would hold true for all local operators. Okay, so I hope this definition is clear. I'll of course expand on that, but this definition immediately tells you that the discrete time symmetry, discrete time translation symmetry of your fluke problem is lost at the level of some local operators. I mean, I'm not saying all local operators would do that, but there should be at least some local operators which should do that. Okay, so this is definition 1. Okay, now I'll go to definition 2, which sounds a bit more abstract, but it's much more related to what I was saying here. It's much more related to this. So you see, the reflection of the fact that there is a broken Z2 symmetry in the thermodynamic limit for some kind of a ferromagnet is that if you look at the lowest states, right, then in a finite system, they actually form these kind of states. Yeah. Okay. So here, something very similar would happen here in definition 2. So if I get a genuine time crystal, what is going to happen is that all eigenstates, now this is very important, all eigenstates of the fluke unitary, U of t, are necessarily macroscopic cat states. All eigenstates are necessarily macroscopic cat states. Now, why do I demand all eigenstates? Because you see, when I try to test for this symmetry breaking dynamically, I said that I should be able to start from any reasonable initial condition. Now, if any reasonable initial condition should show me this thing in a very precise manner, then I should demand something for all the fluke eigenstates. Okay, so if you just think about it, this will be clear to you. I mean, okay, so all the eigenstates here are actually macroscopic cat states. So basically, if you look at, if you just do exact diagonalization on some humongous size, suppose you have a very clever EV code and you have some big computers, suppose you could do it, then you would see that if you diagonalize your U of t for a time crystal, all the eigenstates would be macroscopic cat states. Here I've just shown 2 of them, but of course you might have some state like up, up, down, down, up, up, something, something, plus its partner by square root 2. That's also macroscopic cat state. So all the eigenstates would have macroscopic, all the eigenstates of the fluke Hamiltonian, fluke unitary would have this structure. Okay, so this is an equivalent definition. So why is this an equivalent definition? So let's see. So the reason it's an equivalent definition is the following. The reason again is that my initial state cannot be either this or that or any other macroscopic cat state. My initial state has to be some simple state, which is like at best one copy of this, at best. Okay. So let's say, as I said, this state and this state in particular, let's say these are eigenstates of the unitary operator. Then, of course, by definition, if I add the unitary operator on this state, I'll get an e to the I omega plus here, because I'm considering a unitary matrix, so the eigenvalue has to be of this form, obviously. And similarly, if I take ut minus here, let's say I get a different eigenvalue. That's important for me. Let's say I get a different eigenvalue e to the I omega minus and the same state back, right? Okay, that's important for me. That this eigenvalue is different from this eigenvalue. Okay, for the macroscopic cat states. Okay. See, for this problem, the eigenvalues, which are the energy eigenvalues, are basically the same, right? They're just exponentially apart. But here it's sort of important for me, and you will see that this can be easily managed. Here, these things are actually different from me. Okay. So now start with the physical initial state. So physical initial state is any one copy here. So let's say I start with this. This is, of course, just a toy problem I'm writing here. And now suppose I hit my unitary on this initial state. Now this initial state only has overlap with this fluke eigenvector and this fluke eigenvector. So it's trivial for me to write down the time propagation here. And the time propagation is this, right? So obviously, if you measure any local correlation function, that local correlation function would never synchronize if you look at it stroboscopically. Of course, this n here is a stroboscopic index, right? So n is 0, 1, 2, 3, 4, 5, 6, so on. So no local thing here would synchronize. Okay. So I'll of course tell you how this happens in a real interacting physical system, but this is how I sort of want to view it. So this definition and this definition are equivalent, definition 1 and definition 2. And definition 2 is closer to what we learn in sort of StatNet. So definition 2 is the thing which happens for quantum phase transitions in ground states. Okay. What I'm trying to say is, if you think of definition 2 here, it basically happens for all the eigenstates of the fluke unitary. And then you realize this time crystal. Okay. So now let me take a pause and ask if there are any questions or confusions.
There's a question in the chat box.
Oh, in the chat.
Does N not depend on the local operator in definition 1?
Yeah. So, oh, no. N naught does not depend on the local operator in definition 1. It does not. And here I stressed at least some local operator. This is not in relation to that statement. Here I stress this because you see, there may be local operators for which this thing is equal to this. But as long as find at least one local operator where this thing is going wrong, that's okay. But for a physical system, for a particular time crystal, let's say n naught is 2, then that thing does not depend on the local operator. Yeah. Okay. So.
And so this you can see, strictly speaking, only in the thermodynamic limit, right?
Which one?
I mean, this breaking of time symmetry.
Oh yeah, that's a good point. That's a good point. Exactly true. So that's why I really want to introduce it in relation to this Ising problem, where people have an intuition. So remember I said that in the Ising problem, suppose you're doing a Monte Carlo, right? Or you are doing your dynamics on a computer, right? You will see that there is an exponentially long time scale, after which you will see that the ergodicity would be restored, right? So that time scale is exponential of alpha L. That's what happens for discrete symmetry breaking. And when L tends to infinity, that time scale goes to infinity. I'll show you a numerical plot later where exactly that thing happens. There's a time scale which is going exponentially in system size. Okay. So thinking like this, you see, it's not so different from what we have learned so far. Yeah. So in a finite system, if you wait for an infinite time, of course, there's no time crystal. But if you wait for a time which is smaller than exponential of alpha times L, then there is a time crystal. I hope that answers your question.
Yeah.
Okay, good. So let me go on. So, yeah. Okay. And as maybe I should highlight this once more. The macroscopic cat states here, which are the eigenstates of your fluke Hamiltonian, of course, they have entanglement features which are completely different from short-range correlated states, right? They have entanglement features which are completely different. So one such feature, which is a very nice thing, is the following. So the paper by Else, Bauer, and Chetan Naik, they also showed this thing is happening in the eigenspectrum of the fluke Hamiltonian. So what is this feature? So there's some quantity called mutual information. So in quantum information, there are lots of quantities to characterize the entanglement of a state, right? Because you see, as you know, entanglement is a subtle thing. You might need various different quantities to look at different features of entanglement, right? So the particular quantity that, let's say, the Else and others looked at is called mutual information. So what is mutual information? So the right-hand side is familiar to us. S of A is nothing but I take a pure state, I integrate out everything but A, and then I just calculate my von Neumann entanglement entropy on A. Okay, and that's of course in general a mixed density matrix. So this is S of A. Similarly, that's S of B, and S of A union B is maybe there is A here and maybe there is B here, and they are spatially separated. Okay, then you just integrate out all the degrees of freedom, trace out all the degrees of freedom except A union B. except A union B. Okay. So then S of A plus S of B minus S of A union B, that's called mutual information of A comma B. And that's in general 0 or greater than 0. This one can show. Okay. And this quantity only vanishes if A and B are unentangled among each other. Okay. If A and B are unentangled among each other. Okay. So that means rho of A union B can be written as rho of A cross rho of B. Okay. So yeah. So for these macroscopic cat states, so for these eigenstates, all of them, actually this guy approaches log 2, even if A and B are highly spatially separated. Okay, so that's again telling you that there is some very subtle entanglement contained in these states. Because for simple states, I mean, all reasonable states, you would imagine that this quantity should go to 0 if A and B become spatially well separated, right? So, yeah. Okay. Now, generic interacting systems or fluke versions of generic interacting systems locally reach infinite temperature ensemble. Okay. Therefore, the eigenspectrum of U of P cannot have eigenvectors that look like macroscopic cat states, right? That's an impossibility. So generic fluke systems cannot have time crystals, right? So then MBL comes as our savior, because as I already told you, fluke versions of MBL, particularly at large frequencies, can have localization properties, and their unitary fluke unitaries then need not look like random matrices. Okay, yeah. So yeah, that's the point. So now what I'll do is a trick, and basically it's a very nice trick, and then everything will come out just magically. But this trick is based on something which I sort of introduced in the last lecture towards the end. You see, even in the last lecture, we were saying that, okay, suppose I start with some limit in which, you remember there was a problem, the XXZ problem with disorder, where I said that J perpendicular was 0. If J perpendicular was 0, all the eigenstates were trivially unentangled, and the wave functions could be written in the sigma Z basis. Now I turned on a small J perpendicular, and then of course this is no longer true. The eigenstates are more complicated, but nonetheless, because the MBL survives in this interacting limit, so this is a perturbative statement I'm making now, because and I also made that last time towards the end, but I'm repeating it because I think it's important. Now when you turn on a small J perpendicular, because your final eigenstates, which are MBL states, have area law entanglement, if you try to write a unitary rotation, which is equivalent to diagonalizing your matrix to a eigenvector basis, if you want to think numerically, then that unitary rotation is strictly local in space. Okay, that unitary rotation is strictly local in space, and we sort of wrote a precise equation there in that slide. Actually, it's quasi-local in space. So the point is that that happens because you're just trying to go from product states to area law states. So you can, in some very precise sense, do it by writing a unitary which is in a very precise sense local in space. So basically what I'm trying to say is, even though you're looking at the entire spectrum, there is something like a perturbation that you can do. Okay, that's what I'm trying to say. Remember, in our first few lectures, we said that you cannot do perturbation theory in generic high energy states, because in generic high energy systems, the level spacing is very small. Okay, of course, the level spacing is again very small in MBL systems, but in MBL systems, and this also arose in the question answered last time, in MBL systems, what happens is, if I take any high energy state I, and I hit it with an operator, local operator V might be your perturbation, for example, then you can ask, of course, the matrix element of the matrix element of J with, so let me backtrack. So let's say E of I is a is a eigenstate, and then you are putting a perturbation there, okay, which is making your problem an MBL problem. So the non-interacting thing was J perpendicular going to 0. Okay, so maybe I should use my Jamboard here because I think that's better. So let me just try to do that, because this is sufficiently important. Okay. Okay, hopefully by the end of this talk, you will understand this cartoon picture also, but let's not worry about this now. Oops. So let me go to page 16. Yeah, let me sync it. Okay, it's synced now. So let's see. So basically, what I'm saying is that in an MBL system, if you ask, suppose I have something like this, and this may be the problem with J perp equal to 0. So these eigenstates are very simple, or it may be with J perp being small. So I'm just making a perturbative statement. Okay. So you can imagine this thing either to be a trivial state like this, or you can imagine it as a state of a MBA, which has some area law content of MBA. Okay. Then you hit it with some perturbation, which is local in space. And then, of course, it has a finite matrix element with some other eigenstates, right? Now you ask, can this state and this state have basically the same energies? The answer is no for an NBL. Okay. So with almost probability 1, the answer is no for an NBL. And that protects your perturbation theory. Because usually in a thermalizing system, the reason your perturbation theory breaks down is that even if this number is small, no matter how small this number, the energy denominators that you get are much smaller, right? Because they are exponentially close to each other. But in an MBL, what saves you is that basically, whenever the energy denominators are small, the numerator is precisely 0. You don't have a matrix element connecting this local V to some other eigenstate with almost the same energy. And whenever this guy is reasonably big, order V or whatever your perturbation is, then your energy denominator is also reasonably large, so that in principle you can do perturbation, even for high energy states. Now, this is not a very obvious thing, but that's why I did not try to prove it mathematically. It's pretty hard to prove mathematically, but this is a property of MBL, through which, therefore, you can even think of doing perturbations for the entire spectrum. Okay, so yeah, I hope at least the reason why these divergences don't occur here is sort of okay to you. All I'm trying to say is you might have objected and said that these energy denominators vanish if you do perturbation in high energy. But basically what I'm saying is that for most of these energy denominators, the numerator is strictly 0. And when the numerator is not 0, then typically EI has a reasonably different energy to EJ, even if you're considering the high energy part of your spectrum. Okay, so that's the statement. Any questions so far? I'll now switch to my talk. Any questions from? Okay. Okay, if there are no questions now, then let me use this trick and show you how a time crystal emerges. So I'll start with a problem which I can solve exactly. And then I'll just perturb that problem. And when you perturb that problem, it becomes an interacting NBL problem. And basically, certain features which cannot be destroyed perturbatively remain. And they will be enough for me to argue that the system is a time crystal. That's the route that I'll take. Okay, so let's go on. Okay, so this is my problem here. This is my fluke problem. So you see here, the exponential here that I'm taking, this sometimes in the literature is called a pi pulse. This is a very simple object. You see, just think of an individual spin half degree of freedom. How do I rotate about the particular axis? This is my rotation unitary for a rotation by an angle theta around a particular direction, right? So suppose I want to rotate by an angle pi around the x-axis in spin space. in spin space, then this is the operator that does it. So what does this operator do? If you feed this operator any state, which is written in the sigma z basis, then this operator returns the minus sigma z state to you, right? So you just give me any product state which has, let's say, up, down, up, down, up, down, down, up, whatever combination of spins. You hit that operator to that state, then by definition, you get the reverse of that initial state, right? I mean, all the spins are just flipped. All the SZs are just flipped, okay? So that's part one. What is part two? Part two is I need some non-commuting piece. So here is my non-commuting piece, here. So there is some random ji, there is some random hiz, and there is some random x component here also. You see, this random, so this is like a, what is it? This is like a S equal to half problem with both random transverse and longitudinal magnetic field. Okay. So now, what you do is, suppose I switch off this transverse magnetic field. Then this problem is simple to solve. Well, not completely straightforward, but at least we know all the eigenstates, and then we can compute the eigenvalues because it's just diagonal in the sigma z basis. Of course, if I turn on any small hix, if I turn on any small hix, right, then this problem is not a non-interacting problem, it becomes a interacting MBL problem. That's the crucial bit. You see, let's repeat that again. Suppose I switch off this term. Suppose I switch off this term, then I know all the eigenstates of my problem, right? The eigenstates are all states written in the sigma z basis. So 2 raised to the power L of them. Let's say there are L spins, right? So all of them. So all the eigenstates are area law, right? They're violating ETH, but that's a trivial statement because this is basically a non-interacting problem. But now the crucial thing is, if you turn on a small perturbation like this here, those area law states can be continued to their many body localized versions, because the unitary matrix that you need is basically quasi-local in space. Okay, that's what we sort of did in the last couple of slides in the previous lecture. Okay, so basically these area law states can be continued to the, so these trivial zero entanglement states can be continued to the area law states of the full interacting problem. And we can do that because when hix is small, so more precisely when this is small, we know that this problem goes to a interacting MBL problem in one dimension. Okay, so yeah, good. So this is also going to be important for me later on for this problem. Again, I'll just switch off this coupling. Okay, I'll just switch off this coupling and show you that a certain thing happens. And then when I switch on this coupling, certain things cannot change perturbatively. Okay, I'll tell you that, and therefore I'll get a time crystal. That's the argument. Okay, so right. So good. So let's go on. Right. So I'll switch off this coupling here. So this H MBL is at, if you wish, put a bracket here at H equal to 0. Okay, at H equal to 0, then this is a trivial problem to solve. Okay, so this full problem is trivial to solve. I can just solve it by hand. So that's what I've said here. So I consider the H equal to 0 limit first. At H equal to 0, the eigenstates of H MBL are all, you can write them in the sigma z basis. There's no problem, right? SI, or if you want SIZ, whatever, you can take any notation, right? Take any such state as an initial state, right? And see, these are after all physical states, right? Obviously, because they are completely unentangled, simple to prepare states in a lab. So take any of these as your initial state. And now look at what happens to the system stroboscopically. Now, this is very simple. What happens to the system stroboscopically? So suppose I start with this state. Then when I go to n equal to 1, first the system sees this operator, right? This operator just flips the spins, right? So it does this. And then the system just sees this phase factor. This is just a phase factor because HMBL is basically diagonal in this basis. So it just like accumulates a phase factor. That's it. Nothing more happens. Then when you go to the next fluke step, then of course this thing again switches the direction of the spin and so on. And then the system just keeps accumulating this phase factors, right? So it's very straightforward. So if I give you this physical state, At n equal to 0, it looks like this. At n equal to 1, it looks like that. At n equal to 2, it looks like this. At n equal to 3, it looks like that, and so on. If I give you some other physical state, at n equal to 0, it looks like that. At n equal to 1, it looks like that. At n equal to 2, it looks like that. At n equal to 3, it looks like that. So suppose I give you a simple local correlation function, not a 2.1, let's say a 1-point correlation function. Let's say I go here and measure the sigma z of this thing. So that's my correlation function. That's a 1-point correlation function. So this guy is +1 here. This guy is -1 here. It's +1 here, -1 here. Similarly, it's -1 here, +1 here, -1 here, +1 here. Of course, if you look at this 2-point correlation function, there is +1 here, +1 here, +1 here, +1 here. But I just want to give you at least one operator which is local, and yeah. So this operator does not synchronize, right? And this is a trivial time crystal. Why is it trivial? Because it's a completely non-interacting problem. So you would say, what's the big deal here, right? I mean, this is completely trivial, right? But here comes the non-trivial statement. Here comes the, so yeah, sorry, I had to say one more thing here. And after that, I can introduce the non-trivial statement. So the thing that I want to say is, for this soluble point, for your soluble point, now suppose you ask me, what are the eigenstates of the fluke Hamiltonian? What are the eigenstates of this fluke Hamiltonian? Now, this is, because this is such a simple problem, I can solve it by hand. Okay, I can just solve it by hand. So I'll just tell you how to solve it. And what we'll see is, very importantly, that all the eigenstates of the fluke unitary would be macroscopic cat states. And the two partners, let's say cat state 1 and cat state 2, the two partners, they would have different quasi-energies. Okay, and in fact, their quasi-energies would differ by pi, very important. But we'll see that immediately. We'll just see that. Okay. I mean, let me just take a pause. If there are any questions from anybody, I hope till this part is clear what I'm trying to say. This is anyway, after all, a soluble point. So hopefully this is clear.
So Arnab, this seems true even for a small system, right? Finite.
Yeah. This is a fine-tuned thing, right? So in this fine-tuned thing, this will go on. Yeah. But of course, when you put interactions, then there'll be an exponentially large time scale, after which in a finite system will be.
Okay, so with the so this is if you put on the transverse field, then it's still
correct. So, but yeah, for this trivial fine-tuned problem, even in a finite system, the time crystal survives till an infinite time. But this is a trivial problem, right? So, yeah, okay. So, okay. So now comes the slightly more important thing which I want to extract from this trivial problem or from the soluble limit. So here is it. So how would I calculate the, so yeah, I just give some simple prescription here. So you see, there are two parts here. One is the phase factor accumulated due to this term, and one is this term, right? And HMBL has two pieces. HMBL has this piece, right? This guy. And actually, that's it, because I'm at h equal to 0, right? So, yeah. Okay, good. So, yeah. So, you see, one piece of HMBL is even under spin flip, right? And the other piece is odd under spin flip. Yeah, that's clear. So, that's why I've written it as E plus and E minus, because this plus guy is even under spin flip, and this minus guy is odd under spin flip. There are two parts to your HMBL. Okay, so E plus of SIZ is obviously by definition this, which is obviously the same for the partner of it. So you take any spin configuration and you just reverse all the spins. That's the partner of this guy, and this E plus remains the same for that by definition. But E minus, of course, picks up a sign for the other partner, right? So you can, so I don't go into this in a very elaborate fashion. So you just hit U on this state. Then by definition, you can show that this is what you get. And importantly, this guy changes to that guy because of the pi pulse, right? And the phase factor you put up because of the HMBL. So this is the phase factor, if you just work it out. Similarly, for the other guy, of course, this is also not an eigenstate. So it changes to that. And this is the phase factor that you pick up. Okay, this is the phase factor that you pick up. Okay, so none of the physical states are eigenstates of the unitary matrix, the fluke unitary. So what are the eigenstates of the fluke unitary? If you just work this 2x2 problem, after all, this is just a 2x2 problem, or you can just stare at it and the answer will come out. These are the eigenstates. These are the eigenstates. So these eigenstates are obviously macroscopic cat states, right? Because it's a linear superposition of this macroscopic state and this macroscopic state. Macroscopic state meaning that this state is distinct from this state macroscopically, right? That's what I mean. So this is a macroscopic cat state, right? Very similar to what we were doing here. What we were doing here. Very similar to that. Very similar to that. Okay. So yeah, here. Okay. And what are the eigenvalues? You can just again calculate the eigenvalues. These are the eigenvalues. Now this is important. Sorry, the square root 2 is the normalization of this guy. Okay, there's no square root 2 here. Yeah, but I think it's obvious from the what I've written. So these are the eigenvalues. Now, very important. The eigenvalues of U for the two eigenstates are different. One guy is plus something and the other guy is minus something. That's very important. Okay. So what is this importance about plus something or minus something? It's actually better to look at it in sort of a circle. Why a circle? Because you see, I'm just considering the eigenvalues of a unitary matrix. So the eigenvalues of a unitary matrix are always of the form e to the I theta, and therefore theta, of course, always has a 2 pi periodicity. So you can just represent theta on a circle, right? Because these are quasi-energies, right? So if you just represent it on a circle, then you can see that these guys, this state, so the plus guy in my next slide, the plus guy is when this sign is plus, and the minus guy is when this sign is minus. And there can be a variety of these states, right? Depending on what this state is, right? So for example, you look at some state plus 1. 1 means there is some initial spin configuration which gives you this eigenstate. Then the partner to that has the fluke quasi-energy, which is exactly pi different from it. Like this. You can see it's diagrammatically opposite. I'm just representing it geometrically. Similarly, if you take some other state, right? That of course has a different factor here. So it has a different quasi-energy here, right? It has a different quasi-energy because the quasi-energy depends on which state you are in. But the partner again is diagrammatically opposite here. Okay, if you look at the quasi-energies on the circle. Okay, that's why they're just different by pi. Okay, of course you could have said that they're different by 3 pi, but 3 pi is the same as pi, so whatever. So I'm just representing them as diagrammatically opposite points. Okay, good. So I hope so far this is all clear, right? I haven't said anything tremendously complicated. Now I'll use this entire machinery of this remarkable property of MBL, that you can extend perturbation theory even in the entire spectrum, which is a highly non-obvious statement, right? So now I turn on a small HIX in my HMBL. So remember in HMBL, there was this piece, right? And I switched off this piece. Now I turn it on, but I turn it on keeping this disordered thing to be small. So what do I mean? This magnitude of this H is much, much smaller than HIZ or JI. That is what I demand, okay? So that I can think perturbatively, okay? Right, so if I demand that, then basically what happens is that I've written it in this slide. Basically what happens is that the new unitary that you will get, U of P, the new unitary is of course an interacting unitary. So you will need a computer to solve it, of course, right? Because now it's an interacting problem. You cannot do it by hand. But the new unitary is connected to this old unitary, the new unitary is connected to this old unitary by just a unitary transformation, and that unitary transformation is local in space. Okay, so I have written it more clearly in the next slide, but yeah, I'm just giving you the motivation. And yeah, so this resulting problem is an interacting problem and it has many body localization, right? And the reason for all this intuition is that local in space perturbations perturb only locally in a many body phase. Okay, that's why I can say all these statements. Okay, so here is the more precise statement. So of course this so this guy UF perturbed is the full answer when H is non-zero. Okay, so maybe I should even remove this perturbed from here. I just want to convey the full answer when H is small. What I'm saying is that there exists a local unitary curly U like that, which I can write as e to the minus I times s, where s is a local in space function. So actually, when you do perturbation theory, especially degenerate perturbation theory in quantum mechanics, you learn it like that, right? I mean, you know, in degenerate perturbation theory in quantum mechanics, you do a unitary transformation when there are lots of subspaces, and then you do a unitary transformation, and then you can think of effective theories in these different subspaces. So I think you may have seen things like that in just degenerate perturbation theory in quantum mechanics. And this S is again a local quantity in perturbation theory in quantum mechanics, usual quantum mechanics for the low energy spectrum. And this S can be written order by order as a sum of a local term plus a slightly more local term. So there's an entire hierarchy there. So exactly the same thing would happen here. Okay, and you will be able to write this this thing, the left hand side, which is a non-trivial thing because it's an interacting theory, in this form. Okay, I'm not giving you any proof of that. I'm just giving you a physical motivation of that. Yeah. So where this is the fluke unitary of your original problem. So maybe I'll write it in my notes properly. So HMBL at H equal to 0. Okay. So yeah. Okay. So now comes the key point. Of course, your eigenvectors are changing now. Why are you so your original eigenvectors of your fluke problem were these cat states. Okay, were these cat states. Now the final eigenvectors of your interacting theory would of course change, because you're taking the original eigenvectors, which are these guys, and you're hitting them by some unitary matrix, okay, which is some big unitary matrix, which is some local spatial structure, but nonetheless it's a non-trivial matrix. And so you're hitting these this column vector by that unitary matrix, and then you're getting something else, right? So that something else is not such a simple thing, obviously, right? And it cannot be, because after all, it's an interacting problem, right? But here comes the key point. Whatever that thing is, because you're hitting your original cat state with a local unitary operator, that thing cannot destroy the long range entanglement of the cat state, because the operator that you're hitting it with is a local unitary operator. Okay, so it cannot destroy this long range entanglement. Remember when we were discussing the long range entanglement of the cat states, I introduced the concept of this mutual information, I of A comma B. And for these cat states, when A and B are very, very far from each other in real space, even then I does not go to 0. The mutual information does not go to 0. It goes to log 2. Okay, so this log 2 cannot change to 0. That's a non-perturbative thing. But I'm doing perturbation here. So this log 2 would basically remain log 2. Okay, so it cannot change to 0. It cannot become a short range state suddenly. Okay, so this log 2 stays log 2. And so this guy, as long as this perturbative regime is valid, as long as I'm in this MBL phase and I'm not going to somewhere else, I have proven to you that the spectrum of this unitary, the fluke unitary, has long-range cat states. Okay, so all the eigenstates are macroscopic cat states. Okay, so this is a genuine interacting time crystal. Okay, by my definition too. So any initial state that you start with, that initial state would be a short-range state, but that initial state would have an overlap. So you have to express that initial state in terms of the eigenvectors of the unitary. The unitary are all, the eigenvectors of the unitary are all long-range cat states. So this initial state would have like finite overlap with 2 or more of them. And all these cat states and their partners are strictly separated by pi. So that basically gives you a very precise synchronization breaking. when you go to this interacting problem. Okay, so let me pause here and see if there are any questions. But this is basically a demonstration of time crystals in interacting problems. Okay, so yeah, maybe one needs to think a bit about this, because maybe even though the argument has a simplicity, but the simplicity is of course deceptive in some sense, right? But the entire thing is based on this thing in MBL, that local in space perturbations only, so perturbations which are local in space only sort of have a finite effect over a spatial extent if you're in an MBL case. That is the sort of guiding principle in this entire argument. That principle is very difficult to prove completely analytically. As I said, there's a sort of a almost rigorous proof, not quite rigorous proof, by Imbri in 2014 in one dimension, taking some weak assumptions. But yeah, I mean, yeah. But at least there are physical reasons to sort of see what's happening, and yeah. So, okay. Now let me show you. So this I was just talking and telling you that this thing should work. Now, does it actually work? That's the question. See, this is now an interacting problem. The proof of the pudding is, let's say I do it on a computer and see if this thing actually works. Okay, it's very good that I have given you these sort of reasonably subtle arguments, because a certain thing here doesn't have a strict proof, it's just proved semi-rigorously, and I have sort of used that. So then you would still want to check it on a computer in an actual calculation. Okay, so now here is the actual calculation, again from Else, Bauer, and Naik's paper. So there is a technique called time evolving block decimation, which is basically some kind of a DMRG technique, which you can use in the many body localized space. Okay, so this technique is very well known. The reason you can use it in the many body localized phase well is because to use this technique, you can, so this technique is very good when you are considering states with low entanglement. Now, suppose you want to study dynamics in a thermalizing problem, then the entanglement very quickly reaches volume law, and then basically this technique is very hard to use. But in a time crystal, you're sort of protected by many body localization. So the entanglement does not rise so fast. So you can still sort of use this technique. They use this technique here. They started with some kind of a product state here. Okay. For a system of size 200, that's pretty impressive. They are not doing exact diagonalization, by the way. They are doing something else. And of course, the bottleneck for them is that they cannot go to very long time. Okay, because there is something called bond dimension in these kind of techniques. And if you want to go to very long times, then after a while, this bond dimension explodes. Okay, and then you cannot sort of do it on your computer for a reasonable numerical cost. So they could do it till some reasonable time. But this time scale is much larger than the natural units of your problem. So it's much larger. Okay. So you see, remember, in my original solvable limit, I used h equal to 0, right? That was my solvable limit. Now they use h equal to 0.3. And this graph is for that h. This graph is for that h. So again, you see, if you look at some operators like expectation of sigma x or expectation of sigma y, and oh, sorry, I forgot to mention, they also do a disorder averaging over some disorder realizations, some disorder configurations, when they introduce this random field, right? So, here you see that the the local operator x and the local operator y quickly thermalize. They just go to 0. After all, their fluke ETH value is 0 because that's infinite temperature, and at infinite temperature, these 1-point correlations should go to 0. So yeah, they just go to 0. But if you look at sigma z, then a variant of what I said here, a variant, of course, a much more complicated variant. I'm not drawing the eigenstate in that graph. I'm just drawing a local quantity. The eigenstate does something much more complicated. Okay. But a variant of that survives here. If I'm just looking at the local quantity sigma z, And you can see that the sigma z does not synchronize. You see, because if you look at odd ends, then the sigma z is sort of negative. It reaches a negative value. But if you look at even ends, then it reaches a positive value, right? And yeah, and so this is a time crystal where you have broken this synchronization in this very precise manner of 2t. Okay, so for this problem, this n naught that I was talking about is 2. Okay, so you can of course devise problems where n naught is 3, 4, whatever, but yeah. So this is one important slide which demonstrates to you numerically that if your h is small, still this fx survives. This is a genuine interacting problem now. Okay, right? Now let me show you another slide, which is again conceptually very important. The next slide that I'll show you, the same authors showed the figure using calculations using small system sizes. So there they did not need to do time evolving block decimation. They could just do exact diagonalization. So they literally took the fluke unitary and they could diagonalize. Then they took some initial state. Then they could literally do time evolution till whatever time they want, right? Because now they have the eigenvectors. So here is the graph. Now this graph is very important. So first, let me just tell you what this is, and then I'll focus on what this quantity is. So this graph shows you that there is again an exponentially diverging time scale in a finite system, finite but small system, beyond which the time crystal behavior melts away because the system is finite. Exactly like I said, what happens when you break this Ising symmetry for a ferromagnet and you look at, let's say, a Monte Carlo simulation, right? So here also, there is some quantity they calculate. I'll just tell you very quickly. There's some quantity that they calculate. So maybe I'll tell you that quantity right now. So you see, here is the quantity. So they look at some particular site. So what they do is they start from a random initial product state. So your initial state is some random product state in the SZ basis, some random product state. Okay. And of course, they do lots of such random product states, and that's what this overline indicates. That's the averaging. Okay. And they also do some disorder realizations. Okay. But what they measure is you measure, so this 0 and t, they are sort of running at sort of integer times because they are normalizing with capital T. Okay. So this is whatever is the initial state. Then this is whatever is at time t equal to capital T, capital 2t, and so on. Why do I have this -1 to the t here? To take care of this factor. To take care of this factor, right? Because for odd cycles, this guy is negative. For even cycles, this guy is positive. Of course, the reason that this guy is positive here is I have chosen some initial state where at time t equal to 0, this guy was positive. If I had chosen some other initial state, this guy could have been negative at time t equal to 0. That is why you use the sine function here. Okay, so I hope this quantity is clear. So they just take this quantity and they just plot it as a function of time. Now you see something remarkable here. You see that there is a distinct plateau here. And this plateau has the exponential alpha L scaling in time. You can see that this x-axis is the log scale. So yeah. So this, so as you increase the system size, the system spends more time in this plateau. And then eventually this quantity goes to 0. So when this quantity goes to 0, that means that the time crystal behavior is lost. After all, this is again like a spontaneous symmetry breaking, right? From whatever we have said, this spontaneous symmetry breaking, because exactly like what we are used to in usual phase transitions, there are these cat states when you are looking at the ground state or near the ground state, right? Because the cat state has to preserve the symmetries, but the initial state is something else, and then ultimately the initial state will cover everything. So something similar happens here if you take a finite system size. But the important thing is, exactly like in equilibrium, there is a exponentially long time scale in system size which emerges because this is a discrete symmetry breaking. This is a spontaneous symmetry breaking which is discrete in nature. Therefore, again, there is a time scale which is exponential of L, okay, and that emerges, right? I hope this graph shows that very clearly, right? So, yeah. So maybe I pause here for a minute and take some questions, because then I'll show you something else, again related to this, but something which I find to be even more interesting. So, yeah. Any questions? I hope I've convinced you that if you think in this language, basically many of the things are mimicking what you know usually. It's just that now you want this thing to happen for all initial states, right? So these cat state structures are needed for all the eigenstates of your fluke unitary. And somehow this MBL comes as our savior and lets us protect this cat state structure. Because this cat state structure is there at some soluble point, and then I perturb it, then the problem becomes an interacting problem, right? But because the problem is in its MBL phase, in some sense, I can still think of the perturbation locally in space, but that local in space thing cannot destroy this cat structure of the soluble point, cat state structure of the soluble point, and therefore the unitary fluke unitary of the entire interacting problem also has this structure, and then of course all these things follow. Yeah. So any questions so far?
Hello.
Yeah.
Yeah, I've asked a question in the chat box, but
You can
I'll
ask me
mention it
here.
now.
Yeah, yeah.
Yeah. So in the previous slide, you said that it's hard to evolve the system for long period of time, t by t, t by capital T. But in the next slide, it's going to 10 to the power 12.
Oh, yeah, yeah.
So
But see,
what
yeah, yeah,
exactly was
yeah.
the
Correct,
problem in the
correct.
first slide?
In the first slide, you see the system dimension is 200, right? So I cannot use exact diagonalization for a size of 200 because the Hilbert space is 2 raised to the power 200. That's a huge Hilbert space.
Yeah.
So I do not use exact diagonalization here. I use BMRG kind of techniques here. But in the next slide, I'm not using BMRG. I'm using exact diagonalization. Sorry, not I. Sorry, I mean Else, Bauer, and Nayak. Okay, they're using exact diagonalization. But because they're using exact diagonalization, they are restricted to these systems 8, 10, 12. Okay, but this slide is this figure is very important because this shows you this ergodicity time scale, exponential alpha L. That's why I put this figure here. Is that clear? Why I
Okay.
can go
Yeah.
to
Yeah.
very
Yeah.
long? Yeah. Okay.
Yeah. Thanks.
Of course, if you stick to size 200, you would never see this time scale because that number will be extremely large, right? So, any other question? Okay. So, if there are no other questions, let me go on. Now, let me show you that this kind of a property can not only be stabilized by many body localization in one dimension, it can be stabilized in a generic system without any disorder if I am in two dimension, but only in a pre-thermal sense. Okay, so I find that very interesting, and let me just highlight the key things there. The proof there is a bit more delicate, so I won't go through the details of the thing, but I'll just give you the physical idea. Right? Anyway, we don't have too much time now, so I'll just give you the main physical idea. I find this thing very interesting. So here, of course, you needed this protection by many body localization. Now I'm telling you, if I go to two dimension, and if I don't have disorder, of course, if I don't have disorder, my problem will flow to infinite temperature. But if I choose my fluke problem in a reasonable manner, then I can still stabilize this kind of a thing, this phase. I can still stabilize this phase and for a very long transient time. Okay, so here is the thing. So again, this work is by these three authors again, and I find this paper rather beautiful. It's a bit hard to read, but anyway, I mean, I'll explain some things, and then if people are interested, they can read this paper. Okay, so the idea is the following. So fluke time crystals can be stabilized without disorder in dimensions higher than one or with long range interactions in one dimension. But for simplicity, let's just think of dimensions higher than one. So what do I mean by that? So what I mean by that is, what I'll show you, not show you, just sort of give you the arguments, is that suppose you're in two dimension. So let's think of a concrete problem in two dimensions. Suppose I'm in two dimension, and let's say again think of the transverse field Ising model. In two dimension, the transverse field Ising model is not an integrable problem. It's a highly interacting problem. Let's say I take a square lattice and I think of the transverse field Ising model. But nonetheless, I know that in two dimension, if I pick out any eigenstate, let's say I have some godlike computer with godly powers, and I can do exact diagonalization in 2D, and I again pick eigenstates from the spectrum where the energy is arranged like this, then of course you know that in 2D, if you're below TC, then there is a notion of a phase transition, right? Your Z2 symmetry is spontaneously broken, whereas if you're above TC, the Z2 symmetry is not spontaneously broken. So in particular, let's say I take an initial state, which is, let's say, most of the spins being polarized in the SZ. Then, because most of the spins are polarized along SZ, let's say one way or the other, doesn't matter, then I know that this state has a low energy density, right? When I expand it in the eigenbasis of the two-dimensional transverse field Ising model. Because it has a low energy density, from ETH, I know it has a small temperature. Because it has a small temperature, if I evolve this state for a very long time, under ETH, this broken symmetry would survive. Okay, because the thermal density matrix for a big enough system size would respect that property. Okay. However, suppose I take some other initial state. And that initial state is, let's say, a completely random product state of plus and minus SZs. Then that state I know has a rather high energy near the middle of the spectrum if I took the two-dimensional transverse field Ising model. So that's almost like an infinite temperature state. In that state, the Z2 symmetry cannot survive. So if I just think in terms of ETH and I just propagate that state, I would see that, of course, the symmetry does not survive at long time. This just comes from ETH because I'm in two dimensions. Okay, so now what happens is there is a very clever way to use this in the fluke problem such that if I take my first initial state, what was my first initial state in a 2D problem? Let's say in the transverse field Ising model. So the first initial state was, let's say most of the spins being up. If I take the first initial state, then for even stroboscopic time, I would see sigma z doing this, whereas for odd stroboscopic time, I would see sigma z doing that, exactly like this graph. But in this graph, if MBL protects the phase, this red line and green line goes till infinite time, if MBL protects that phase. Here, MBL is not protecting the phase. So what is going to happen is that there will be a pre-thermal time, which will be exponentially long in some parameter of the system. That's why I'm drawing it on a log scale, but a finite time scale. After that finite time scale, it's just exponentially long in some fixed parameters. It's not exponentially long in the system size. So it's different from this. Okay, it's just exponentially long in some couplings of the system, in some parameters of your Hamiltonian or your fluke Hamiltonian. But nonetheless, there is a very long time scale. After that very long time scale, this guy will go to 0 and this guy will go to 0, right? Because because the time crystal cannot survive till infinite time. Okay. Whereas if you start with an initial state, which is like a random initial state, then basically you won't get a time crystal here, but you will still get some pre-thermal thing here, and then you'll go to something else. Okay. So I'm sort of going to tell you what this protocol is. So of course, this pre-thermal thing here is finite because it's a reflection of the fact that in that Ising problem, the symmetry is broken. Okay, that's the reflection of that. And after that, it just goes to something because then it's a more complicated thing, and even that symmetry is lost, and it just goes to the trivial fluke ETH. Okay, so in the remaining time, I'll just motivate that. Okay, but this depends on your initial condition. If you take most of the spins being polarized, you will see this in the thing that I'm going to tell you. Whereas if you take a random initial state, you will see this. You will not see a time crystal, okay, in 2 dimension. So what do I want? So yeah. So unfortunately, I'll rush through a bit, but hopefully if you read the slides and some of the later literature, if you're interested, then you will get many of the things. So there is a very well-known version of fluke prethermalization, which is understood at large frequencies, large drive frequencies. So what do I mean by large drive frequency? Suppose my driving frequency, so the driving frequency is nothing but the inverse of T, capital T. So the driving frequency is suppose large compared to all the local energy scales of my Hamiltonian. After all, I'm using a local Hamiltonian, so there are all kinds of local energy scales. So more precisely, if omega d is much, much larger than J local, where J local denotes the energy scale of local rearrangements of the degrees of freedom in an interacting problem, then necessarily there appears a large transient time, T star. So some kind of a time like this, T star here, okay, which is exponential of omega d divided by J local. That's why it's exponentially large in some couplings of the problem. It's not exponentially large in system size. It's some finite number, but it can be made very large. Okay. So there's a large time, a transient time T star, below which the system is in a pre-thermal state, both here and here. Here, of course, it's doing something extra, but here also it's in a pre-thermal state. Okay. And this pre-thermal fluke state is well described by a so if you do some kind of a perturbation theory, like a Fluke-Magnus perturbation theory, you can actually truncate that perturbation theory at some optimal order. Then this is a local Hamiltonian. This pre-thermal state is well described by a truncated Fluke Hamiltonian, so a local in space Fluke Hamiltonian. And the system does not heat up to infinite temperature till that time scale, because this guy, this truncated Fluke Hamiltonian, appears as a new conservation law below this time scale. Above this time scale, this conservation law is lost. So it's an approximate conservation law. Above this time scale, this conservation law is lost. Okay, good. Now, very importantly, maybe you will later realize when you think about the notes again, very importantly, the dynamics of local observables can be described accurately by this truncated Hamiltonian, even when your time scale, when your time scales are within the pre-thermal window. This is a very non-trivial statement. Why is it non-trivial? Because you see, suppose you truncate your Hamiltonian. If you evolve your system with this truncated Hamiltonian, like e to the minus I h f t, of course, you get a completely different wave function to the wave function that you would have gotten with the full Hamiltonian, obviously. Because the full Hamiltonian is some different operator and this Hamiltonian is some different operator. And you're doing time evolution with two different operators. You'll get different answers, obviously, right? But very importantly, if you're only looking for local observables, not for all global properties, if you're only looking for local observables, then this truncated Hamiltonian actually describes the unitary evolution very accurately in the pre-thermal time window. This is actually a non-trivial and a very subtle statement. That's why I've just written it. So maybe if you think about it later, you will understand why this is non-trivial. Okay, good. So physically, why does this time scale emerge? That's very easy to see. So you see, why does the Fluke problem heat up to infinite temperature? Because the system keeps absorbing energy from your drive, but the energy can only be absorbed in steps of omega d, right? Because there's a frequency scale, right? So, but here I've told you that omega d, the scale is much, much larger than J local. After all, the system has to do local rearrangements to absorb energy, right? It has to change to something else, and only then it can sort of absorb something, right? So you see, to absorb even one quantum of energy from the drive in this situation, when omega d is much, much greater than J local, physically, the system has to do some very correlated local rearrangement, okay, which takes many, many steps. If you think in terms of a perturbation, which takes many, many steps. And therefore, that local rearrangement, that highly local rearrangement, which involves many, many, many correlated steps, would take exponentially long in this parameter. Okay, so this is a perturbative argument. Okay, and this is indeed true from more careful studies. Okay, good. Now I come to the thing which I want to tell you about in the remaining time about this thing, and then I'll conclude my lectures for this Bangalore school. So I want to tell you how this emerges. So now consider the case where the driving frequency omega d is much greater than all but one of the local scales of the Hamiltonian. Okay. So the driving frequency is not greater than all the local scales, it's greater than all but one of the local scales. So there's one local scale which is comparable to the driving frequency. All the other terms in your Hamiltonian are small. So here I have written it schematically. So your time-dependent Hamiltonian is h naught plus v. So v encapsulates all the terms. So let's say the scale of v is lambda. So lambda times t is much, much less than 1. So v encapsulates all the terms where omega d is much larger than the scales here. Okay. Importantly, h naught. So now I want some particular property in h naught. I want some particular property. H naught, whose scale I would show you is comparable to omega d. So the scale here, the sort of energy scale here would be comparable to omega d. This h naught has a special property or a special form. Suppose you just calculate the unitary time evolution using h naught for one cycle. Okay, so this is the expression for that. Then I want h naught to have, okay, since I'm running out of time, let me just focus on m equal to 2. Then I want the property that x square is identity. In fact, this can be any integer, but any integer greater than 1. But let's say I just want x square to be identity. So I demand this property. Okay. So if h naught has this property, then you can actually show that again something like pre-thermalization survives. You can again show that. Okay. So the way you show that is the following. You go to the interaction picture. So remember in quantum mechanics, we have these standard 3 pictures, Schrodinger, interaction, and Heisenberg. So you just go to the interaction picture where Vt, this term, is basically the interaction term. So this term gives you the unitary rotation, and this is the interaction term, right? So, so then you just do some standard things, which I have written down here. You can work out those things. After you do those standard things, you can again show that for this problem where this h naught has this special property, then there again emerges a timescale t star from the standard arguments that I told you. From the standard argument that I told you, this argument, there again emerges a timescale t star, which is exponential of omega d renormalized, if you wish. So omega d renormalized is just renormalized by this m. So there's a factor of 2 here for the problem that I'm going to consider. Okay, that's it. So yeah, so I'm skipping some steps, but this is reasonably easy to figure out. Okay, so there's again a pre-thermalization physics here. This pre-thermalization physics would be lost if this h naught does not have this property, Okay, because then I cannot use this argument here. Okay, but now I need something more. So that is, now this is a bit more complicated. This was shown in that paper by Else, Bauer, and Nayak. Okay, but I'll sort of run through it. The thing is, there can be cases where this x, where this operator x can be interpreted as a symmetry in some higher dimension, in 2 dimension, and then you get interesting pre-thermal phases. Now we already know how to construct such an operator. Remember the pi pulse that we discussed? What was the pi pulse? The pi pulse was just a spin flip operator. It was just a product of all sigma ix. So if you go back to the pi pulse, if you go back to the pi pulse, where is the pi pulse? Here. If you go back to the pi pulse, you can just easily show that this is just product of all sigma ix. Now, what is product of all sigma ix? Product of all sigma ix, if you just give it a state in the z basis, it just inverts all the spins. But this is the sort of symmetry that is broken for the 2-dimensional ferromagnet, right? So I already know how to sort of incorporate these things. So basically the point is, if this x can be interpreted as a symmetry operator, which can be broken in some higher dimension, then you get very interesting pre-thermal physics. Okay, so if this x can be spontaneously broken. Okay, so now let me just give you the recipe of this time crystal, this pre-thermal time crystal, which does not require disorder. Okay, so the reason this happens is this is the non-trivial thing. This is slightly hard to prove. I won't prove it here, but I wrote the statement here. Basically, you can show again through some local unitary transformation that this interacting unitary of the full problem in the pre-thermal window, not everywhere else, in the pre-thermal window has an emergent symmetry. How do we know that? Because after doing this unitary rotation, which is again localized in some real space, but not because of MBL, this something else. Okay, the thing which is inside has this very beautiful structure. It's x times, so x is your symmetry operator, x times exponential of minus I dt. Now, amazingly, this d, which is an interacting problem, this d has some interacting terms, but this d commutes with this x. Okay, so what that means is that in the pre-thermal window, basically your unitary time evolution sees this hidden symmetry of x. Why do I call it a hidden symmetry? You see why? Let's go back here. Let's go back. Let's go forward. I'll tell you why this is a hidden symmetry. So this is my explicit fluke Hamiltonian that I take. So my h naught is a term like this. Okay, it's a simple term, and the integral of this time evolution satisfies this. Then it's obviously your pi pulse, and because the integral satisfies this, then sorry, was there some question? Maybe not. Okay. Because this hx satisfies this, so from this equation, the scale of hx is comparable to omega d. But the rest of the terms, the v, which you can for simplicity take them to be static, okay, are these. Now you see this term respects your up-down symmetry, Ising symmetry, but this term breaks it. This term breaks it. But the important thing is, as I already told you, this term and this term are small compared to your frequency scale. Then in your fluke Hamiltonian, in your d here, these kinds of terms would disappear. All terms which break the Z2 thing would disappear. Your fluke Hamiltonian, now this is subtle, I didn't explain it. The fluke Hamiltonian in the pre-thermal regime would just be composed of terms like this plus ... Okay, and all those other terms, they'll all preserve this up-down symmetry. And this u naught is x by construction, okay, because it's the pi pulse, okay, right? So then what happens, and this is the final cartoon picture which I want to tell you about. Then what happens is, literally, when the system enters the pre-thermal thing, why does it take some time to enter the pre-thermal thing? Because first, the system needs to thermalize with respect to this many-body Hamiltonian, right? Now, this is that initial time scale here. This time scale, which the authors had written as pre-thermal here, is your initial state thermalizing with respect to this Hamiltonian. Okay, but you see, now comes the fun part. When you think of the unitary time evolution, suppose you think of the unitary time evolution for even cycles. Let me just transform my basis and just go to this basis of V, so that I don't need to keep talking about these guys. I mean, that's not so important. The important thing is this x times this guy. Now, suppose you look at u squares or u4 or u6 after the thing is thermalized. After the thing is pre-thermalized to B, then you see x square or x4 or x6, they're all identities, right? Because you are doing these spin flips twice, right? So then if you look at even stroboscopic times, the system would just thermalize to the state of, to whatever is the macroscopic thermal state of this guy in the pre-thermal window. And after that, it'll flow to infinite temperature. But you see, if you look at odd times, let's say u of n plus 1t, then x raised to the power n plus 1 is x, where n is an even number and then there's a plus 1. So x raised to the power n plus 1 is x, because x raised to the power n is identity. And then you see the effect of this symmetry breaking, right? Because this operator x would just flip you from this thing to this thing. So basically the picture is that your system goes here, and then of course for the even cycles it sees this, and for the odd cycles it sees that because of the x hanging there. It's literally like your system is being hit by some operator which just flips everything. So you just move through these guys back and forth, back and forth. So it's like a limit cycle, if you wish. And then, of course, after the pre-thermal window, which I talked about, where all this physics is true, after the pre-thermal window, the system realizes that, oh, MBL is not protecting me. I have no disorder. The system realizes that. And then the system happily flows to infinite temperature. But before the system happily flows to infinite temperature, you have realized a time crystal depending on your initial state. If you take your initial state, which is, let's say, most of the springs being polarized, then on general grounds in 2D, you know that that finite temperature state breaks the Ising symmetry. So you do this. But if you take an initial state which is all randomly polarized, then it has a very high energy density with respect to this D, and then basically you are in a single well potential, and then you don't get this limit cycle. Okay, so this is the realization of a pre-thermal fluke thing. And by the way, I did not put the references. I'm sorry about that. Both of these things, the pre-thermal thing as well as the time crystal with MBL protecting it, both of them have been realized beautifully in experiments. Okay, so yeah, so maybe I'll stop here, and hopefully I've given you some flavor of this very interesting field which has several open questions. So maybe I'll stop.
So Arnab, I just had one question. I mean, so this in these systems, it's in some sense, it's not like you're breaking like continuous time translation, because like it already had a period T, correct. And then you're just So it's not like a space crystal.
No. So Abhishek, as I said, you cannot break continuous time translation. So maybe I didn't stress it. There are some no-go theorems also if one thinks about it hard enough. So yeah, continuous time translations cannot be, so it's like a weaker thing than a space crystal. Yes. Yeah. Was there any question? I could hear some background, maybe not, I don't know.
Yeah, no, there's no other, I think. Okay, so maybe we'll stop here. So thanks Arnab for a really beautiful set of lectures, and which is really I mean a lot of new interesting areas have been covered, and I think I'm sure people will want to explore this more in the future. Yeah, so thanks a lot really for all the effort.
Thank you.
Thank you, Arnab.